All right, yesterday was the first day. We went over some of the stuff. We went over some discrete math review. And today we're going to start hopping into some of the core content of the course. So today will be a very brief overview of what languages are, what grammars are, and what automata are, so that we can dive into significantly more detail about specific kinds of each of these, potentially starting later today or tomorrow based on time. So we're going to start with a very broad overview of these concepts, and you may have some preconceived notions about what these concepts are, but we're going to be looking at them at a very abstract level because we want to be able to zoom all the way out and determine, all right, what are these concepts at their most abstract form? So a language has an alphabet. An alphabet must be a finite, non-empty set of symbols. We're going to use a capital sigma, talk about the alphabet. You're probably used to seeing this representing sum, but in this class, it will represent the symbols in the alphabet. An example we could say is the alphabet AB, or the alphabet 0, 1, representing binary, or the alphabet representing the lowercase and uppercase English letters, and the digits 0 through 9, but it could also be the digits representing hex. You put these characters together and you get a string, a finite sequence of characters. Each of those characters will be pulled from the alphabet that we're denoting by sigma. In this class, we're going to be setting characters most frequently as those being lowercase letters toward the beginning of the alphabet, and strings we're going to be setting as lowercase letters toward the end of the alphabet. So here is a string that we will call U, and it's made up of the characters A, B, B, A, which each come from the alphabet denoted at the top of the slide. Another example, the string V could be equal to B, A, B, B, A, B, B, A, B, A, A, B, A, 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 A. And each of those again come from the alphabet. So if you read a textbook on this material, usually A, B, C, etc. name characters, and U, V, W, etc. name strings. You will be familiar from prior classes about some things we can do with string concepts within programming languages, like concatenate them, reverse them, find substrings within them, figure out how long they are, determine whether or not a string is a prefix or a suffix of another string. We can do all of those in automata theory as well. A string is still just a string. The empty string, instead of being denoted by open close quotes or however you might have seen them before, is going to be defined in this class by lambda. So lambda just means the empty string. And this is for consistency with the textbook, consistency with other things that you might go find if you were to do that. I don't generally like using too many symbols that don't directly relate to the concept, but I also want to make it clear if you go do some outside research or read the textbook. The reverse of a string is going to be denoted by W to the capital R. So W will be the string. If we wanted to reverse the string U, we would have U to the capital R. And that just stands for reverse. If we want to repeat a string n times, we will say it's the string name raised to the power n being the number of repetitions of that string. So U squared would be ABBA, ABBA. Questions about notation for alphabets, strings, things you can do to strings? This will all become useful as we start looking at automata, which just I don't want to say it, they simulate the use of a computer. So being able to read input is important to be able to, we need to be able to parse a string to be able to do so. So we need ways to describe how we're going to be parsing that string if we're going to be able to determine, like, write a machine that accepts a particular language or rejects stuff that's not in that language. Questions? All right, more preliminaries. We have our alphabet, which we're denoting by capital sigma. So we can define sigma star, that's a superscript star. That's denoting all of the possible ways that we could combine different characters from that alphabet to produce any number of strings. So if the alphabet is AB, then we could have lambda, the empty string, A, B, AA, AB, BA, BB, AAA, etc. There's no limit to the length of these strings, but you could define sigma star to be any possible string that could be made using any number of those characters. Repetition allowed. We have sigma plus. Sigma plus just means that it's the same thing as sigma star, but we're removing the ability to have the empty string. And we'll find that we have a few cases where we care about representing all of the strings in using a particular alphabet where we don't care about the empty string. So we need some way to communicate that. One thing to note from this is that even though our alphabet is finite, when we look at the closure and the closure minus the empty string, those are always infinite. You produce a set that has an infinite number of elements. Why is that? What's the intuition behind why the size of those sets, their cardinality, is infinite?
Because you can use any amount of any character in the alphabet.
Yeah, even if the alphabet size is 1, right? You can just have any number, define the length of that to be any number, and you get the set of positive integers, which we also know to be infinite. So we can map an infinite set to another infinite set. And so we know that this will always be infinite. So now we can define a language. We defined an alphabet and we defined strings on that alphabet, but a language is going to be some subset of sigma star. Because usually we don't want to represent every possible string. If, for instance, English is a language, but not every possible set of some allowable characters in the alphabet produces something that has meaning in English. ZY, BA, BA, ZX. It's an example of a string in using the characters of the English language that has no meaning in the English language. So we define some subset of strings within this alphabet and repeating characters within this alphabet that are within a particular language. We can have a sentence within a language, and this just means that it is some string that is in the language. So cat, for instance, is a string in the language English. Some examples of this that we might care about in this class, we'll say that sigma is AB, so the only characters that we care about are A and B. The language is A to the N, B to the N. So first, let's figure out what are some strings that are in sigma star. AB, that's in sigma star. It's also in the language. Note that there's not necessarily overlap between, there will be some overlap, but there are some things that are in sigma star that aren't necessarily in the language. This was a great example of a string that's both in sigma star and in the language. What's something that's in sigma star that's not in the language? C doesn't contain a character that's within the legal alphabet. So we need to have some number of symbols that are within this, within AB, but they cannot adhere to A to the N, B to the N.
BA.
BA, sure. That's some repetition of A's and B's that it does not conform to the rule A to the N, B to the N. First, is it clear what A to the N, B to the N represents? We have for some number N, that number of A's followed by that number of B's. Question?
You say the empty set would also count?
Yes. If we're talking about sigma star, then we want the empty string lambda would also be in sigma star. Examples of sentences in L. AB was one of them. What else? AABB. AABB, yep. AAABBB would be another. What about lambda? You technically want this to be defined n is greater than or equal to 0. But if it is defined without that, then yes, lambda would be in the language. How many sentences are in L? Infinite. Yeah, there's no dictation for what n could be. It could be any natural number, positive integer or 0. And then we already did this one, examples of sentences that use the alphabet that are not in the language. BA was an example of this. ABB would be an example of this. AAB would be an example of this. So there are an infinite number of sentences in the language, and there are also an infinite number of sentences not in the language. We know that languages are sets, right? They can be an infinite set, but there's still a set of things. It's either contained or it is not contained within the language. So we can now define languages by using set operations, union, intersection, and difference. And it works the same as the set review that we did yesterday. We can take the complement of a language and define the complement of a language as everything that's in sigma star that's not in the language. So the universal set, according to a language, is going to be the set of strings that can be produced by characters in the alphabet. We can also define the reverse of a language as take everything that is legally in that language and accept everything that is the reverse of one of those strings. So if we wanted to take the reverse of A to the N, B to the N, what would be some strings in the reverse of that language? So since lambda was in the language, the reverse of lambda is still lambda. The reverse of the empty string is the empty string. We decided that AB was in the language. So if we reverse AB, we get BA. So that would be in the reverse of the language. AABB was in the language. So BBAA would be in the reverse of the language. And with a little bit more analysis, you come to the conclusion that B to the N, A to the N is the reverse of the language A to the N, B to the N, because all strings that adhere to the reverse of A to the N, B to the N are going to start with NBs and end with NAs. That will not always be the case. You can't just take the symbols and flip them like that, but it was the case this time. We can define the concatenation of languages. So we have some language L1 and some language L2. We need L1, we want to define a string XY, the concatenation of that, where X comes from the first language and Y comes from the second language. Does that make sense? Any questions about that? We can also define concatenation n times or repetition. So we can define L to the n being repetitions where we have the language concatenated with itself. L to the 0 is lambda, L to the 1 is just L. But after that, we can take L squared, L cubed, L to the 4th. If you want the star closure of a language, L star, this is going to be the union of everything L concatenated with itself any number of times. So L to the 0, union L to the 1, union L squared, union L cubed, and we're going to call that the star closure. If you want to remove just the empty string from that, we get the positive closure. So just like we had sigma plus instead of sigma star, the only difference was we removed the empty string. The positive closure of a language just removes L to the 0, which is just the empty string anyway. So removing the empty string from the star closure gives you the positive closure. And again, this is just a massive term dump. It's not the most important thing at the moment, but we do want the ability to reason about and discuss languages. How are we doing? Any questions about languages? How to define languages at the highest level of abstraction? We will be coming back to different classes of languages and being able to construct state machines that represent certain languages in a bit, but this just gave you the very brief basic overview of what is a language, what are things that we can do to languages, and strings over languages. The next big topic that we're going to talk about in the class is grammars. And you can imagine it's very similar to the concept of an English grammar or a programming language grammar that you might have seen before. What is a grammar? Any preconceived notions? Yeah.
Rules for how strings are formed.
Yeah. We want to be able to determine whether or not a particular sentence is well-formed or not. And of course, that well-formed has to be with respect to a particular language. Something that's well-formed in Java is not necessarily well-formed in English. Go take aside someone randomly on the street and start talking to them in Java, and they're going to look at you like you're insane. So we'll start with an English grammar, just to give you an idea of how we're going to be defining rules within grammars, because it will be very important to be able to, throughout this class, start constructing grammars that represent languages. So this is a very, very basic generalization of English. This is not a whole English grammar, but we will take a part of it to define. This arrow is going to be the part that is on the left is defined by the part that is on the right. So we're going to define a term sentence, and that is between angle brackets, representing that it's not a character within an alphabet, but it is a generalized idea. It's a name or a term that we have for a construct. So a sentence is a noun phrase, another abstract idea, followed by a predicate, another abstract idea. Whenever we have these abstract ideas, we need to further define them with rules in the grammar. So we will further define a noun phrase to be this abstract idea of an article followed by an abstract idea of a noun. A predicate can just be defined as a verb. Finally, we can define an article as either the string the or the string a. A noun can be defined by the string boy or the string dog. And a verb can be defined by the string runs or the string walks. So taken together, all of these rules define what is or is not legal in this incredibly simplistic view of the English language. So think about how this grammar is formed. Think about the sentences that could be formed with this grammar. And is "the boy runs" an example of something that would be acceptable in this grammar? Could we have some kind of derivation from this grammar that would help us to be able to produce "the boy runs"? How could we do that?
Maybe break down phrase into article now.
Yeah. So we're going to start with this concept of everything starts out being a sentence, right? We just want to prove that by following rules in this grammar, we can deduce the sentence. This grammar can create many, many different sentences, but we want to show that one of those sentences is "the boy runs." So a sentence must be defined by noun, phrase, predicate. So we will now we can replace noun phrase with article noun. So we will have all right, now we can replace article with either the or a. Which one do we want to pick here? The, because we want to produce "the boy runs." And so it would make sense to make this all right, noun can be either boy or dog, so we want to produce something that represents the sentence. So we're going to choose boy from here. So we have and we can continue to, once we have these terminals, we don't necessarily have to continue writing them. You can kind of just start drawing lines down to say that we've reached a leaf. You can start to envision this as a tree. But we'll replace the predicate with verb. And we'll replace the verb with runs. So we end up with "the boy runs," and we followed only rules from this particular grammar, and we generated this sentence. So if grammar is well formed with respect to a language, it should be able to generate every sentence in that language. So we will be talking significantly more about grammars, how grammars relate to programming languages, since programming languages also have grammars for them. Spoken languages have grammars for them. Abstract languages, like A to the N, B to the N, have grammars for them. We'll also be talking about the kinds of rules that you need to use in particular grammars to be able to produce particular classes of languages. Any questions about what a grammar is or a derivation within that grammar? Reasonably important concept for now. We good for this to go? What is an example of a sentence not in the language by this grammar? Yeah,
The girl ones.
sure. Yeah, if there's a string that we can't produce, like for instance, there's no rule between noun and girl. This grammar is very sexist. Then you can't derive it. If there is no rule specifying a particular order, like for instance, we could have dog runs a. You could not actually produce that in this grammar. That would require a different ordering of your noun phrase and your predicate, your articles and your nouns, and you would not be able to generate something that does not follow the noun phrase predicate rule. So if you have a complete grammar, it will define every possible sentence in a particular language. That doesn't mean that there's only one grammar for a particular language. You can define multiple different grammars that all specify exactly that language. But if you have a complete grammar, then you get this rule where if the grammar can generate a particular string, then it is in the language. And that's a very important rule to be able to follow for particular grammars. And this will become necessary if you start thinking about the concept of a compiler and what the job of a compiler is. A compiler asks the question, is a particular set of symbols that you typed as an instruction something that has meaning in a language like Java? Int x equals 5 semicolon is something that is legal in Java. So we could reasonably build a grammar for the Java programming language to determine, is this instruction well formed? And then you could write additional rules that would translate the rules that you've generated into machine instructions. And that's exactly what the goal of a compiler is at a very high level. I just want to get you thinking about how this is going to be applied from the beginning. I'm showing you as this really abstract example, but where we will be going with this is that we want to be able to understand and write our own compilers and the ability to translate something at a very high level into something at a very low level. One other thing with a complete grammar, if the grammar cannot generate the string, then it is not in the language. So we have a perfect segregation of strings in the language, strings not in the language, and the segregator is the grammar. If it can be formed by the grammar, it's in the language. If it can't be formed by the grammar, it's not in the language. We want to start with very general concepts like sentence. Sentence is a very general concept. And the parts of speech that we talked about, a noun, a predicate, those are all parts of sentences. So you're going to start breaking down these abstract concepts into more and more specific concepts. Eventually, you get to the irreducible building blocks of the language. In English, you end up with words. So grammars do definitely exist for major programming languages. Any guess as to the level of complexity? If you wanted to guess how many rules there are in a grammar for Java, for instance? This is the Java grammar. So we will go to this. Here we go. Grammar below defines the following Bacchus-Nar form style conventions. We'll talk about what BNF style grammars are. I know this isn't very readable, but my point is, it is long. And you can see that we have different classes like assignment operators. And we know that assignment operators can be equals, plus equals, minus equals, times equals, divide equals, ampersand equals, vertical bar equals, caret equals, percent equals. We have bit shifts. We have all sorts of legally defined assignment operators that you can use. So being able to discuss grammars and produce grammars will be useful if you ever care to write your own compiler, write your own language. There are lots of different compilers out there for different languages, and fun people write fun languages. Does anyone know of any joke programming language out there? There are quite a few of them. Have you run across any? One of them is LOL code. Let's see if we can find some very basic programs in LOL code. Why does this go to Edge? Hate it. Here we go. Here's an example of a program written in LOL code. LOL code is a complete logical language. You can write and portray anything that you could in Java in this language. It's ridiculous. It's not particularly widely used, as you might imagine, but it's interesting to know that you can create your own languages. Joke languages exist. The worst one that I've ever run across is called white space. The only characters that are allowed are spaces, tabs, new lines, and carriage returns. Every program looks the same. You have to highlight the program to try to figure out what those characters are. But of course, you can build any logic that you can with this. Should you? Absolutely not. It's ridiculous. But the idea is that just because there are a set of programming languages out there doesn't mean that there isn't a better one out there in your head that could be produced. But it's not good enough to just define the rules of the language. You need to have the ability to convert the languages in your head logically into an assembly language or a machine code that could be useful. So enough fun for now, but there's lots of fun that we can have with this. All right, so here's how we're going to define a grammar. It's as a quadruple. We have 4 components, V, T, S, and P. We have a finite set of objects that we're going to call variables. This was the sentence, the noun phrase, the predicate, the verb phrase, everything else that we used in the prior example. Those are variables because they don't represent anything within the alphabet or the language. They're these higher level constructs that represent abstractions within that language. We also have a set of objects we're going to call terminal symbols. Terminal symbols in the prior case was the string the string boy, something that is a string in a language. They're terminal because they don't need further explanation. They become parts of strings in the language. We have a start variable. It's a member of the set of variables where everything begins. Notice how in the prior example, we had sentence, and every possible, is this string in this language, yes or no, is going to start with this most abstract start place sentence. Everything in English, every sentence in English is a sentence. It defines itself. Finally, we have a set of productions, and those are each line of the grammar. So the productions are the sentence equals noun phrase predicate. So that is one production of the grammar, the list of rules that you use to and select some subset of or repeat some subset of them to be able to generate a string that's in the language. Each one of those rules is called a production. So again, this is how a book would define a grammar. It's a quadruple. Questions about the formal definition of a grammar? Yeah,
So does this joint mean that the two things do not have any elements?
yeah.
Question.
Yeah,
Sorry, my mind blanked and went over productions. Can you just go through them again?
yeah. So a production is basically every line here. So this is a production, this is a production, this is a production. It's a way of taking something that's more abstract and producing something that is less abstract. And eventually you get down into something that are elements of the language. All right, so that's a grammar. Let's make a simple grammar. So here is the quadruple from the prior definition. Here are our productions. S usually just stands for start, the starting rule. And you can define it in multiple different ways. If you define something like S arrow ASB and S arrow lambda, this allows you to say you could take either one. We'll talk about non-determinism in a bit, but this is basically a non-deterministic grammar in a way that says if you can do it, then it's in the language. So here would be a way to generate the string AABB. We take the start symbol. The start symbol is going to follow this rule where we have A capital SB. Note that the non-terminals, these productions, these rules, they contain capital letters, and then the letters that are within the alphabet are lowercase. And this helps you as you produce the string to be able to determine what is a non-terminal and what is a terminal. Non-terminals need to be further specified, and by the time you only have terminals, then you have the string in the language. So we take S, we apply the rule ASB. We take this S and we expand that into ASB. Note that this box right here is that box right there. So sorry, that's the S. So we have the A, this was the old S, followed by the B, but we've expanded this S into that ASB. And then this S becomes lambda and just goes away. And you can see that that's one possible string that we could produce with this grammar. If we iterated through every possibility from this, we would get the language that this grammar represents. Does that make sense? Question?
Where does the lambda go?
So lambda just represents the empty string. So it'd be like a concatenation of, we have A, B, B, we have something in the middle that's going to turn into the empty string, where you might be used to seeing the empty string. And if you concatenate AA empty string BB, you just get AABB. So this rule just basically says we can replace S with nothing. We chose to replace S with ASB, ASB, nothing. Excellent questions. Other questions? Does that make sense to everyone?
Another question, sorry.
Yeah.
Within that grammar part at the very top, we, just so I can easily differentiate what's happening there, we have an S within curly braces and the S without. I'm just trying to look at.
Yeah, so this represents a set.
Right, yeah,
So the only non-terminals that we have in this grammar is S. There's no other thing. It would be like, one way you could do this is to do like, you could define this as a capital AB, and then further define capital A as something else. And if we did that, then this would have S comma capital A. So this becomes the set of all non-terminals. And then we only can define a single non-terminal here to be the starting symbol. We can't start either with S or with A. We have to always start from the same position. So this just defines which one of these symbols is used as the start symbol. Very good question. Yeah,
Will there always be just one start symbol?
Yes, if you had other start symbols, like you had a grammar where you could either start with an A, something, a B, start with something, and you wanted to do something like this, you could just write an additional rule that was S can be capital A or capital B. And then you have a single start symbol. So they would be logically equivalent. You can always just factor out a single symbol that goes into one of those non-terminals. Other questions? Really good questions so far. So now the question is, what is the language defined by the grammar? So think about the different kinds of strings that this grammar could produce, and then try to represent it in terms of some language specifiers using something like A to the N or B to the N or something like that. How can we represent the language accepted by this grammar? I'll give people a couple minutes to work on that. Is that a question or an answer?
Answer.
Let's give people just a little bit of time. What do we think?
Would it just be A to the N, B to the N?
Yeah. So we've seen this language before, A to the N, B to the N. We could start with just the empty string, so the empty string is in the language. The next thing that we could do is apply, I turned your sound off. We could apply this rule followed by this rule, where we would have AB. So we had lambda, we have AB, we can apply this rule, this rule, this rule. Note that this rule terminates the whole thing, and it's the only way to terminate the whole thing. So we can apply this rule any number of times, but as soon as we apply this rule, we're done. So if we apply this rule once, we generate AB. If we apply this rule twice, we generate A, B, B, just like we did down here. We could apply the rule 3 times and get A, B, B, B. And continuing this process, we would see that the language that this grammar represents is A to the N, B to the N. Does that make intuitive sense to people? Yeah.
So this makes intuitive sense currently, but I know another part where you define like language and stuff like that.
Yeah.
We had AN, BN, like AN times BN. But we can like essentially move letters around and like kind of like put them how we'd like to. But in this example, there's like a strict ordering in a way. Is there like am I correct there, or is there something I'm missing?
Yeah. The A to the N, B to the N defines the order. There has to be some value for N, and it's going to be a natural number. So 0, 1, 2, 3, 4, 5. So the alphabet in this case is AB, and sigma star over this would be any possible arrangement of A's and B's. But the language we're defining is just a subset of the strings that you could get by concatenating those letters. Just like we have English letters combined that make no sense in English or are not a word. Like XRN, I think, has no value in English. But they're legal characters put next to each other. If we wanted to define a particular language, it's going to end up being a subset of that. And this is one such subset of A's and B's. Is some number of A's followed by exactly that same number of B's. 0 or more. So this grammar defines if you can produce something with this grammar, it's going to be in this language. If you can't produce it with this grammar, then it's not in this language. So it's a complete grammar for the language A to the N, B to the N. All right. Knowing proof methods. What proof method could we use to prove this? Does anyone remember back to your discrete math kinds of proofs? I'm not actually going to go through a proof. I'm not going to require that you know proofs for the course, but just being able to identify which proof method you could use to prove that this will always generate A to the N, B to the N. We've used kind of intuition so far.
Induction.
This was an exact, beautiful example of where you would want to apply induction. We have a basis step, right? You could use either of these as a basis step. And then an inductive step would say, assuming that you can generate A to the 1, B to the 1, how do you generate the next one? Assuming you can generate A to the N, B to the N, how do you generate A to the N plus 1, B to the N plus 1? And the way to do that would be saying, just apply this rule one more time. If you do that, you generate the next one. And then induction would, dominoes would fall for the rest of that, and your proof would work for any value for N. All right, we have just a few minutes. We can get started with this. We'll probably go over the answer next time, but how about a grammar that generates the language A to the N, B to the N plus 1 for all N greater than or equal to 0? Use the start symbol S, that's usually what we will do. So your first rule will be S is defined to be something. You can define multiple rules with S. You can use other non-terminals, but I don't think you'll need them. Question or an answer?
Kind of a quick.
Questions are good. What's the
So
question?
with that one, would you create a new variable and have it be like that variable B, and then whatever variable, like let's say B, you would have as A B? Well,
You could. Question?
an answer.
Let's wait just a bit for people to come up with a solution. It's excellent that you have an answer, though. So one thing to note is this is very similar to the last one. We just need to stick an extra B on the end of everything that was generated by the last grammar. So how could we generate a rule to do that? What would that look like? I think I will actually have people work on this between today and tomorrow, and we'll come back tomorrow with an answer. Any last minute questions people have before we dismiss for the day? All right, I will see you all tomorrow.